Welcome to this explainer. Today, we're unraveling what is, frankly, the ultimate mathematical detective story. We're going to explore how a seemingly simple act, just arranging discrete vectors on a grid, actually acts as a mathematical failsafe. It literally prevents the physical universe from ripping itself apart. It's a stunning, absolutely crucial connection between abstract combinatorics and physical reality. And we are going to break down exactly how the equations make it happen.
Okay, let's dive into this structured, equation-driven journey. We'll start with Rota's basis conjecture, move into the Adelic flag variety, then the Swan conductor explosion, the synchronization matrix, cohomology and geometric bounds, and finally, the arithmetic mass gap.
Section 1, Rota's basis conjecture explained.
So, Rota's basis conjecture essentially asks us a question. If you have a set of independent vector bases, can you always arrange them into a perfect interlocking matrix grid where every single row and column forms a valid basis? Now, you might be wondering why this is so hard. Well, historically, the sheer combinatorial complexity of swapping and exchanging these vectors in higher dimensions made it incredibly difficult to prove. It's like a giant puzzle with billions of moving parts. To resolve this massive complexity, we need a paradigm shift. We have to translate it out of discrete combinatorics and into the continuous, geometric language of the Adelic Langlands program, creating a global topological boundary condition.
Section 2, the Adelic flag variety.
Look on the left here, we have our standard combinatorial bases in a vector space over the rational numbers, but to apply our heavy-duty geometric machinery, we actually lift this vector space up to the global flag variety. You see that big script X on the slide? This space is defined as the general linear group over the Borel subgroup, which, simply put, represents a specialized set of upper triangular matrices. In this higher geometric space, arranging vectors into a matrix isn't just a grid puzzle anymore. It corresponds choosing a valid, smooth cross-section of this complex product variety.
Section 3, the Swan conductor explosion. Okay, so what happens mathematically if Rota's conjecture fails? Well, if there's no valid cross-basis arrangement, the geometric cycles on our flag variety literally fail to intersect. Following the top-to-bottom flow here, that creates an irresolvable topological obstruction. When we pass this broken geometry into our J-theory variational flow, which is the mathematical engine trying to stabilize the space, it completely jams up. Because the charts cannot be glued together, the flow can't converge. The result? An infinite geometric curvature spike. In the automorphic domain, this acts as raw, undamped energy density.
And that brings us to this equation, the universal arithmetic syndrome coordinator, or the global epsilon factor. Notice the specific parts of this equation, especially the exponent on the far right. See that term, capital S, lowercase w? That's the local Swan conductor, and it acts as our ramification defect tracker. If those local Sato-K parameters process that infinite curvature spike we just talked about, this Swan conductor term absorbs it, acting as a massive multiplier that forces the entire equation to react.
And this brilliantly illustrates the apocalyptic math we're dealing with here. If the Swan conductor goes to infinity, that diverging exponent instantly shatters the global functional equation. The underlying field computer just cannot process an infinite global error phase shift. Breaking this formula would actually require our finite vector space to become infinite, which violates the Noetherian constraint, a strict mathematical rule requiring finiteness. So the field theory explicitly forbids this. The system mathematically vetoes the failure.
Section 4, the synchronization matrix.
To prevent that mathematical explosion, we need an engine to bind everything together. Let's deconstruct this block diagonal matrix. This is the Adelic flag integration matrix. It computes the precise arithmetic intersection numbers of our base configurations across all those prime numbers. Think of it as the ultimate global interface. It ensures that any discrete vector exchange we make locally is strictly harmonized by global automorphic reciprocity.
Unpacking this matrix layout a bit further, let's focus on one expanded local block. Notice the contrast here. Along the diagonal, we have the unramified Sato-K eigenvalues. Those represent our stable, independent bases. But look at the off-diagonal entries, the omega coefficients. These govern the phase transformations required to transition from one basis configuration to another. If these off-diagonal terms aren't perfectly aligned, the entire system collapses. Now, direct your attention to this rather intimidating integral computing that omega exchange coefficient. It integrates over intersecting cells using a Fourier-Mukai kernel. Mathematically, this acts like a detective projecting a constructive interference pattern. It is a massive filter, smoothing out that chaotic topological curvature we saw earlier and forcing those disjoint basis flags to actually connect.
I know that previous equation was a lot, so to prevent cognitive overload, let's break the mechanics of this universal phase-matching filter into 3 clear steps. First, we identify the Bruhat-Schubert cell intersection. That's the geometric space where our vector configurations actually overlap. Second, we apply the Fourier-Mukai kernel, which acts as the filter. And third, this results in off-diagonal curvature optimization, transforming those chaotic basis combinations into balanced, harmonized waves.
So the crucial point is that the total global determinant must identically equal 1. If bases are scrambled, the cross-basis entries vanish, and boom, the Swan conductor explodes. But to maintain a determinant of exactly 1, the global field equations enforce an exact phase calibration, driving all those scrambled off-diagonal phases perfectly to 0. This leaves us with a totally clean, unipotent grid, just 1s on the diagonal and 0s everywhere else, meaning Rota's conjecture is literally forced to be true to maintain this balance.
Section 5. Cohomology and geometric bounds.
Let's look at the structural constants that physically bound these intersections. In this cohomology multiplication grid, the Kuhneth formula at the top breaks our massive space down into manageable tensor products. And to calculate those flag overlaps, we use the de Mazur operators, also known as Schubert polynomial operators, shown below. Rather than simple numbers, these are differential operators that iteratively multiply geometric sheets together. They extract the Littlewood-Richardson coefficients, telling us exactly how many valid ways these vector bases can intersect. Look at how the formula on screen proves that reality acts as an exact mathematical filter. If Rota's conjecture failed, we'd fall into a divergence trap, an infinite chain of permutations. But the math strictly caps the combinatorics. It proves that higher-order non-basis permutations yield coefficients of exactly 0, which cleanly forces the intersection index to exactly 1.
Let's move to and see how this builds to Section 6, the arithmetic mass gap.
This is the climactic moment where abstract geometry dictates physical mass. Using the Cohn's-Chomsky spectral action principle, physical mass, that m-squared term, isn't arbitrary. It emerges directly from the log derivative residues of the universal partition function, displayed right here. You can think of this as the fundamental barcode of spacetime. The combinatorial vectors we've been tracking all this time mathematically modulate this exact mass pole.
Contrast these two equations side by side. Uncoordinated flags cause the Swan conductor to diverge, which mathematically forces the physical mass gap to explode to infinity, creating a physical singularity where matter just couldn't exist. But under the coordinated phase, our Fourier-Mukai filter tames that infinite product into a manageable Dirichlet series. It shifts the mass pole into a stable, discrete constant.
Now what's really interesting about this slide is what happens when we apply this unipotent boundary condition. The mass shift reduces to the log derivative of the Riemann zeta function, and evaluating those limits yields a completely stunning result. The emergent mass gap squared equals the background mass squared plus the Euler-Mascheroni constant. A fundamental, universal constant that bridges discrete and continuous mathematics drops right out of the necessity for combinatorial vectors to form a grid. No way, right?
Let's summarize this 4-stage pipeline. We started with independent matroid bases. To avoid infinite geometry breaking, they had to be organized by flag variety intersection matrices. Then, the Fourier-Mukai phase synchronization smoothed out all the errors. And this exact mathematical requirement directly produced a stable arithmetic mass gap shifted by the Euler-Mascheroni constant. Physical matter literally cannot condense without this perfect combinatorial basis alignment.
So, if resolving a puzzle about arranging discrete vectors into a grid is a fundamental mathematical requirement to prevent the physical mass of the cosmos from exploding to infinity, is math just a description of reality, or is it the engine? Think about that and keep exploring.